Welcome back everyone. In this lecture, we will actually compute the Killing form for GLN and SLN very explicitly. So, we will actually do the direct computation as well as use the theory to compute. So, let us actually recall what is the Killing form. So, here is the definition, which is denoted by cup of G of x comma y. So, this is given by the trace of at Gx composition at Gy, okay, and it is a form on the space G. Okay. So, here is the immediate observations. So, the cup of G is symmetric G invariant bilinear form. So, the Cartan criterion says, the Cartan criteria tells you that G is semi-simple if and only if the form, the Killing form is non-degenerate. Okay. So, now recall that if we have this cup of G is non-degenerate, so then we can actually look at the corresponding kappa G tilde, which is a map from G to G star, which is given by x goes to the kappa of G of x comma dash, and this map is G module map, which will be isomorphic. Okay. So, this kappa tilde is G module isomorphism. Okay. So, in particularly we have kappa of G non-degenerate implies that G is isomorphic to G star as G modules. Okay. This is very important observation. So, now if we start with G being simple module, simple Lie algebra, so then that implies immediately that the adjoint representation, okay, is irreducible. Okay. So, that means G is irreducible as a G module. So, G is irreducible as G module. So, we are talking about the adjoint representation. Okay. So, now simple implies semi-simple. Okay. Simple is contained in semi-simple. Okay. Now, if you put them together, you can see that. So, you have this kappa of G which is non-degenerate. So, that will imply that G is isomorphic to G dual. Okay. G is isomorphic to G dual. So, with these conditions, you can see that the space home G, G comma G star, which is isomorphic to the invariant forms on G. So, that is one dimensional. So, this is what Schur's lemma says. Okay. So, this way we can conclude that, so this space of G invariant forms of this simple Lie algebra must be one dimensional. So, what is the conclusion? Conclusion is the space of G invariant bilinear forms must be one dimension for simple Lie algebras G. So, in particularly one can take G to be SLN, then we can see that the space of G invariant bilinear forms that must be one dimensional for SLN. So, now there are actually obviously two different uh, G invariant bilinear forms one can construct for SLN. One is the Killing form. So, we can take the Killing form. So, which is, if you think about it, it is not that easy to compute, because we are actually working with the adjoint representation. So, whenever you consider this add x map, which is a map from SLN to SLN. So, to compute the trace, you are indeed actually looking at that n square minus 1 times n square minus 1 matrix. Okay. Then you are computing the trace of that. So, it is a very hard calculation to compute the Killing form. Okay. But now using the theory, you can easily see that you have the Killing form and you also have what is called the trace form. So, how the trace form is defined? So, you can actually define this trace form from SLN to SLN, SLN cross to SLN C using what is called the natural representation. So, note that the natural representation Cn, that is also irreducible as SLN module. So, Cn is an irreducible SLN module. Okay. But anyway, as far as you have the module, then you can actually define the corresponding trace form. So, you can take x y and then map it to trace of x y. So, the trace of x y is computed as a product of matrices. So, x y makes sense as a matrices. So, you take the product x y and then take the trace of that. So, that is what the trace form that comes from this natural representation of SLN. So, you have these two forms. So, then the general theory that tells you that G invariant bilinear forms that form a one dimensional space. So, in particularly these two forms must be scalar multiple of each other. Okay. So, it is not hard to prove that this form is G invariant. Actually, we have proved it for any V being G module. So, the Cn being SLN module. So, this trace form becomes G invariant, that is obvious. So, now in particularly we have, if you are interested in computing the Killing form of for SLN, then that is exactly equal to some lambda times the trace form of SLN. Okay. To compute the value of this lambda, it is enough to actually compute it on some particular choices of x and y. For example, one can take x to be E12 and then y to be E21. Then if you just do the computation, then we can get that kappa of SLN of E12 E21 is going to be exactly equal to lambda times the trace of E12 E21, but the product E12 E21 is exactly E11. So, E11 is the matrix with the 1 on the first 1 entry and 0 everywhere else 0. So, that means that the trace of E11 is just 1. So, that implies that, so the lambda is exactly equal to the value that you compute for the kappa of E12 comma E21. Okay. So, this way you can actually reduce your computation to only some particular values. So, actually we are going to write down the formula for the general matrices. So, I will leave it to you to check what it is actually. So, one can prove that this lambda is exactly equal to 2n. So, this is, I will leave it as exercise, and we are going to do the more general computation for GLN. So, it is not very hard. Okay. So, let us actually do the computation for GLN. So, I already told you how one can use the general theory to reduce the computation for SLN, but SLN and GLN differs by only the central element. So, now central element is actually not that hard to compute the action of the central element. So, that is why like the computation of SLN will immediately tell you that how to compute it for GLN. So, maybe I will leave it that as exercise, use this to compute the kappa of GLN for general x comma y. So, you have to write x and y as sum of elements from the basis that you get it from SLN and adding the identity. Okay. So, then it will become clear what it will be. Okay. For example, x you write A times the identity matrix plus some x dash that comes from SLN, and then y if you write it as B times the identity matrix plus y dash, then the kappa of GLN of x comma y is exactly using the linearity. You can see that this is exactly kappa of identity times identity. Okay. AB will come out identity plus kappa of identity comma x, sorry, y dash plus kappa of x dash the identity plus kappa of x dash y dash. So, you can now compute what it is, okay, because if you think about it, we are only looking at the adjoint maps. So, add of this n by n matrix identity matrix will be 0. So, add of the identity is 0. So, that is why like you can see that all the computation will become elementary. Okay. So, this is something I will leave it to you to check. Now, let us do the general computation, and then I will convince you that we have the exact formula by doing the general computation. So, let us recall GLN is given by direct sum of C E I J, where I j just varies over all 1 to n. So, now what is E I J? This is the ijth elementary matrix. Okay. So, this is the elementary matrix whose ijth entry is 1 and all other entries are 0. Okay. Where ijth entry is 1 and all other entries are 0, all other entries are 0. So, note that if I take Eij EKL, the product is going to be EIL with the delta coefficient JK. Whenever j equal to k, it will be EIL, or otherwise it is 0. So, this is very important formula. So, this is immediate from the action of Eij on the basis. Okay. So, now let us use this formulas and then compute how one can apply this add of these basis elements on general basis element and then write down the formula. So, if we take add of Eij, add of EKL and then apply it on EGH. So, we are only interested in computing the trace. So, we can do the computation on the basis only. So, this is going to be exactly the bracket Eij, the bracket EKL comma EGH. So, note that the bracket EKL EGH is going to be EKL EGH minus EGH EKL. Okay. So, this is going to be exactly delta LG EKH minus delta HK EGL. Okay. So, now if you substitute it back, then you get add Eij, add EKL on EGH is going to give us exactly the following terms. So, this is exactly Eij comma delta LG EKH minus delta HK EGL. So, which is going to give you lots of terms. So, let me just write it down. So, first you multiply this with this, then you get delta JK E. So, let's just you are anyway going to get this coefficient. So, delta jk, delta lg, and then eih you get. Similarly, minus delta hi, delta lg, ekj you get. Then minus delta jg, delta hk, eil you get, plus delta li, delta hk, egj you get. So, this will be the term. So, now if you call AGH as the coefficient of EGH inside this sum, okay, add EIJ, add EKL, and then EGH. So, basically we are looking at the diagonal terms, okay. So, where the diagonal terms will be the coefficient of GH, okay, EGH inside this. So, that is the ith term should be same. So, I is GH, okay, this is exactly the EGH. So, then what it is? So, if you just write it in terms of using this formula, so you can easily see that. So, this is exactly delta GI, delta JK, delta LG minus delta GK, delta HJ, delta HI, delta LG, and two more terms are there, minus delta GI, delta HL, delta JG, delta HK, plus delta HJ, delta Li, delta HK. So, now we are interested in the trace, okay. So, the kappa of GLN of EIJ, EKL we can just compute. So, then we can actually by linearity we can extend it to any basis element. So, now this is going to be exactly summation AGH where GH varies, okay. So, if you take this and then you run it over all GH and then sum them, then exactly you will get the following formula. This is going to be 2n times delta IL delta JK minus twice delta IJ delta KL. So, this is the term that you get at the end. So, you are running over all GH and then summing it over, and then you can see that all the indices, because all of them are the deltas, okay, just get cancelled and you will get only these terms. So, now if you just think about it, so what are these terms, okay. So, this is basically some products of the terms are there. So, this is actually the trace of EIJ, this is the trace of EIJ, this is the trace of EKL, because there is delta IJ, delta KL. So, now if we take this thing, so this is just the product, okay. So, this is you can think it as the product EIJ, EKL, the trace of EIJ, EKL. So, basically you can rewrite the kappa of GLN of EIJ, EKL. So, we have to write it in everything in terms of EIJ, EKL. So, this is 2n times trace of EIJ, EKL. The product of this is same as this, minus twice the trace of EIJ times trace of EKL. Okay. For example, if we want to compute it for E12 and E2n, so which is what we needed for SLN calculation, then you can see that the trace of this E12, E21 is exactly equal to, so you are going to put E12 here, E21 here. So, this is going to be E11. So, this is 2n. So, this is E12, E21 which becomes E11. So, the trace of E11 is 1 and here the trace of E12 which is 0, again trace of E21 that is also 0. So, this is 0, this is 0. So, you get exactly this. Okay. So, now by actually using the linearity for any x and y from GLN, you can see that the cop of GLN of x comma y is exactly 2n times trace of x y minus twice trace of x times trace of y. So, this is a very hardcore computation, but anyway it is good to do it once. Okay. So, this is the explicit formula for the killing form of GLN. So, now if we think about it, if we take x being just the n by n identity matrix, so then you can see that the kappa of GLN of this 1n comma x, okay, maybe just call it y. So, then this is 2n trace of y, then minus twice. So, the trace of the identity is going to be n, again this is 2n trace of y. So, this is going to be 0. Okay. So, this is just kills all the elements y. So, that means this n by n identity matrix, this is in the radical of the bilinear form. Okay. So, this is in the radical of the bilinear form. So, the radical by definition those x in GLN such that the kappa of GLN of x comma y is 0 for all y in GLN. Okay. So, that proves that radical is being non-zero and that means the form is degenerate. Okay. The form GLN is degenerate. But the form is actually non-degenerate when you actually take SLN, and it is not hard to see. Actually, SLN is nothing but the orthogonal complement of this n by n matrix. You can take the orthogonal complement of kappa of GLN with respect to the kappa of GLN of this identity matrix. Okay, this is just an element. So, basically what is SLN? SLN is those x in GLN such that the kappa of GLN of identity n comma x is, oh sorry, this is not the, oh SLN is the orthogonal complement of the usual form. Okay, I need some editing here. So, this part should be cut. So, we have proved that the kappa GLN is not degenerate, but from the general theory one can see that kappa of SLN is non-degenerate, but kappa of GLN is degenerate. So, one can actually see that for the various subalgebras, okay, how to compute the killing form. Okay, again one can work with GLN and then see, like for example, if you take, so maybe I will leave it as exercise. Take this standard Borel and other nilpotent subalgebra of that. Okay. So, let us take the n by n upper triangular matrices, the set of all n by n upper triangular matrices so compute the kappa of Tn. Compute. So now you can also take the set of all n by n strictly upper triangular matrices and then again one can compute what is the killing form of this. Similarly, like diagonals also one can compute. Take the diagonals, the set of all diagonals again compute. Okay, I will stop here and we will continue with the Casimir construction of the Casimir element in the next class. Thank you.